Okay, my name is Swami Gupta. I'll take up for you the structural analysis part of our civil engineering. In structural analysis, what topics we are going to study are this one. First, we have trusses. In your second year and third year of our civil engineering, on the trusses we have studied four topics. First one is analysis of statically determinate trusses. Here you have learnt about method of joints and method of sections. This what you have studied. Some of you have studied in first year engineering mechanics itself, analysis of trusses, where you have used method of joints and method of sections. Statically means using equations of statics. Equations of statics, strength of materials, engineering mechanics, sirs might have told you. Equations of statics means sigma x 0, sigma y 0 and sigma m is equal to 0. So, using equations of statics, you can determine, what we can determine is the support reactions, the member forces in the trusses, everything we can find using equations of statics alone. If you can find everything, all unknown reactions, member forces, if you can analyze, analysis means finding the forces, axial force, shear force, bending moment. If you have to find them, then it is called analysis. So, analysis of statically determinate trusses means using equations of statics alone, you can determine all the unknown quantities. That analysis we call it as those structures we call them as statically determinate trusses. In this chapter, we study about method of joints and method of sections. This method of joints and method of sections, two methods, they are actually same only. A particular case of method of sections is method of joints. You will take equilibrium of a joint and find the member forces. Then that is method of joints. Method of sections means you will take equilibrium of a section of a truss and find the member forces. So, we call it as method of sections. Method of members also is there. That method of members, you use it for the analysis of the frames. Analysis of frames means the frames where the intermediate loading on the members also are there, then you cannot call it as a truss, it becomes a frame. So, for analysis of frames, you have another method called method of members. That engineering mechanics they discuss about the method of members. Okay. Now, second point is, second chapter, deflections in statically determinate trusses. We use statically determinate again. We use using strain energy method. Or unit load method. Strain energy method or unit load method both mean the same. Then why we should study the deflections? As we have studied in strength of materials deals with three aspects of the structures. First one is strength. Strength of a material means it deals first, you will learn about the strength. There you have four types of loading: tension, compression, bending and twisting. So, accordingly 4 chapters you have studied first. Then you have the stiffness. Stiffness means any structure that you build must be first, it should have the capacity to take the loads. That means strength must be sufficient enough so that it will not collapse. Equally important is the stiffness. That means the deflections must be well within the limits. If we know how to calculate the deflections, then we will know how to control the deflections. That means if deflections are more, we can reduce them by, if you know how to analyze, how to find the deflections, by increase the member size or something we can do and reduce the deflections. So, deflections or stiffness criteria is also equally important. Supposing that we have built one slab like this, say, this slab has the capacity to take the loads. That means strength is sufficient. But if it is not stiff, if it deflects too much, then the people who stay there will not be comfortable. Serviceability criteria, it will fail, means it cannot service us. That means when you are moving on the structure, if it deflects too much, you won't be comfortable. Sometimes any machinery equipment you are keeping, let us say, then if it deflects too much, then the shafts or beams that if they bend, then the purpose for which you have built that machine components, they will not serve. So, that is why the equally important criteria is the stiffness criteria. That is why in strength of materials, first 4 chapters are allotted to the strength concepts: tension, compression, torsion and bending, right. Then accordingly bending stresses you have studied, shear stresses, then torsional stresses you have studied. So, they deal with the strength concept. Then you have studied the stiffness criteria, deflections. Deflections by using the Macaulay's method of double integration, strain energy method. Then you have the moment area method. There are conjugate beam method. Many methods are there that you have learnt under the criteria stiffness criteria. If you know how to calculate the deflections, then you will know how to control them to increase or decrease. Strength of materials, you have studied the deflections of cantilevers, simply supported beams, fixed beams, propped cantilevers, etc. Now you will learn how to calculate deflections in the trusses. Okay, we use again same strain energy method only, or that method also we call it as unit load method, because we take the help of the unit load concept. So, that is why it is called unit load method. Okay. So, that is the reason why we learn the deflections in statically determinate structures. Then we have analysis of statically indeterminate trusses. Again you will use strain energy method. Using strain energy method or unit load method. Statically indeterminate trusses means using equations of equilibrium you cannot determine. So, you have to take additional conditions called compatibility conditions. Such compatibility conditions you will get from strain energy method. That is why this method is also called compatibility method of analysis, or method of consistent deformation, or force method of analysis. All mean the same. In your strength of materials, you have studied in each chapter one compatibility condition we have used, and all those methods that you have done in strength of materials, they come under compatibility methods or force methods. First chapter you have learned along, you have both ends fixed rod is there, let us say, subjected to some axial pull in between. Then one member elongation is equal to one member contraction. So, elongation in AC is equal to contraction CB, like that you have done. SM, many problems you have solved. Those methods are, you have taken the help of the compatibility. Compatibility means a relationship between the deformations to maintain the continuity of the structure. So, since you are taking the compatibility condition, that method we call it as compatibility method of analysis. Then after that you have studied in the flitched beams, theory of bending stresses chapter, flitched beams, they are statically indeterminate to 1 degree. That means ds is 1, that means one compatibility condition is required. What compatibility you have used in the flitched beams is the radius of curvature of bent up steel beam, radius of curvature in the wooden beam, they must be equal, because both bend like a single element. That means radius of curvature of both the members is same. So Fletcher beams DS is 1, so one compatibility condition you have used, strain in concrete is equal to strain in steel is equal to strain in wood. Then accordingly that comes from the radius of curvature in wood is equal to radius of curvature in steel. Then thin cylinders, wire wound thin cylinders you have studied. What is the compatibility condition? Circumferential strain in the cylinder is equal to circumferential strain in the wire. And thick cylinders also at the combined 2 or 3 cylinders are inserted one within the other, say. Then at the circumference, circumferential strain must be same. So like that in all the chapters we have used one compatibility condition, we managed the problems. Extension of that is indeterminate trusses. We take the compatibility condition which by using the strain energy method or unit load method and analyze the indeterminate trusses. In the exam, the indeterminate trusses statical indeterminacy or static indeterminacy will not be more than 1. If DS is 1, then we can complete in 1 minute time, otherwise we will not be able to manage such problem. So, simple questions only they will ask you which will take not more than 1 minute time. Indeterminate trusses. Next, fourth one is influence line diagrams. For statically determinate trusses. Influence line diagrams means these diagrams are graphical representations of variations of reaction, shear force, bending moment, etc. as a unit load is moving from one end to the other end of the truss or for that matter any structure. When a unit load is moving from one end to the other end, how the reaction or shear force or bending moment gets influenced. If you plot that influence as a graph, we call it as influence line diagram. Why should we draw those influence line diagrams? Those influence line diagrams tell us where we should keep the loads so that you will get the worst effect for that given quantity. That means you are drawing influence line diagram for bending moment, say, where you should keep the load so that bending moment is maximum at that particular section. If you design the section for that maximum bending moment, for any other loading, naturally it is less bending moment, automatically structure will be safe. So for that maximum magnitudes of reaction or shear force or bending moment, when the loads are moving, for what position of load you will get maximum shear force or maximum bending moment. If you know, for that maximum bending moment you will design that section, then this structure will be safe. For different sections we have to draw influence line diagrams and decide where we should keep the loads to get maximum quantities and design for those quantities. Okay. So these influence line diagrams for determinate trusses we have to draw. In your second year of your civil engineering, these two topics you have studied: analysis, method of joints and sections, deflections. Then third year you have studied about the indeterminate trusses and influence line diagrams. Some of you have studied in the second year, second semester itself. So we have 4 topics on the trusses: analysis, deflections, again indeterminate trusses and influence line diagrams. Here we will also draw as an introductory thing for the cantilever beams, simply supported beams, etc. for determinate structures only. Next, we will also draw influence line diagrams for statically indeterminate structures. In these indeterminate structures, you will learn how to draw influence line diagrams for propped cantilever, because it is indeterminate structure as you have learned in SM. Then you will learn about the how to draw influence line diagrams for fixed beams, continuous beams and also the frames. We will take the help of Muller-Breslas principle to complete this one within maximum of 30 seconds time. In the examination, whether we take a GATE or civil services or engineering services, no question takes more than 30 or 40 seconds time. Such simple questions only they will ask us in the exam. You only have to be thorough with your fundamentals, be clear about the concepts, basic concepts, enough. All questions that you get in the exam, you will be able to answer. So, for indeterminate structures, we take the Muller-Breslas principle, finish off in 30 seconds time any question that they ask in the exam. Next, we will take deflections in statically determinate frames. Again, statically determinate frames only we will find the deflections. Again, using strain energy method. Strain energy method or unit load method. This unit load method comes under force method of analysis. Okay. Wherever you are using unit load means it is a force method or compatibility method, because that is derived for such cases only. So, deflections in statically determinate frames. Then we will take analysis of continuous beams and frames. That is indeterminate structures. Analysis of indeterminate structures. In this indeterminate structures, you will learn moment distribution method, you will learn slope deflection method and matrix methods. In the exam, whatever they give you on the continuous beam or a frame or any indeterminate structure, if they give you, if you know about MDM, slope deflection method, moment distribution method, slope deflection method, or if you know the matrix methods. In matrix method you have flexibility matrix method, stiffness matrix method. If you know these three methods, any question they give us in the exam, your maximum time that you can take is 45 seconds time. A 2 marks question takes only that much, not more than that. Okay. So, this is about the analysis of continuous beams and frames. Next we will study after this analysis of cables. Cable is a special type of a structure where it can only take tension. It cannot take compression, it cannot take bending moment. Based on this analysis of cables, we have 3-hinged and 2-hinged arches. 3-hinged and 2-hinged arches, the basis for those arch analysis was the cable analysis. We will see how the 3-hinged and 2-hinged arches are analyzed. There we will learn how to draw influence line diagrams for the horizontal thrust, how to draw influence line diagram for bending moment in the arches. This is 3-hinged arch is a statically determinate structure, 2-hinged arch is a statically indeterminate structure. So, complete analysis, how to draw ILDs, everything we will learn here. Again, those things are not new. You will learn from Muller-Breslas principle itself, no new concepts. We will see how we will complete them within our stipulated time. Next, we have approximate methods. Approximate methods in structural analysis. In this you will learn about portal and cantilever methods. We must learn about this portal method of analysis and cantilever method of analysis. These approximate methods, portal and cantilever methods, are useful when the multi-storied frame is subjected to horizontal loads only at the joints. The applicability of this portal method and cantilever method is, for the frames all joints must be rigid, loads must be horizontal and applied only at the joints. Okay, like wind load, earthquake load analysis, we will go for the approximate method. Also, which we have taken up in the steel structures, I have given you one concept about the design of battens or design of batten analysis, that is a frame analysis. We take the that means IS 800 2007 has taken portal method of analysis and derived the expression for the longitudinal shear force in the batten and bend moment in the batten. So, that is why we have to know about the portal methods, because the understanding of this we use again in the design of steel structures. Okay. Next, we have stability of structures. In this stability of structure, we will learn about static indeterminacy, ds, dk and stability. Three aspects we study here. Stability of structures, you will study what are the conditions necessary to make a structure in stable condition. The meaning of stability of a structure means, without applying any force, or even if you apply a force, if the structure undergoes rigid body translation or rigid body rotation, we call it as a mechanism. Mechanism or unstable both mean the same. So, stability of a structure means what are the conditions for a structure to be in stable condition. So, those things, the conditions for that, under what circumstances a structure will be in stable condition, a spatial structure or a plane structure or a truss or a beam. So, those all such structures, the conditions for stability we will learn in this topic. Then after this we will take up the matrix methods. Here we will study about the flexibility, and stiffness matrix methods. In this flexibility and stiffness matrix methods, most of you have in your engineering, this matrix methods of structural analysis is a optional subject. That means it is an elective subject. But since they have asked included in the syllabus, so only fundamentals they will ask you. That means a 1 by what is a how to build a stiffness coefficient, or a 2 by 2 stiffness matrix or flexibility matrix, how to invert a 2 by 2 matrix and analyze a simple structure, which will take say 1 minute time maximum. So, using that matrix method, we have analysis of beams, trusses and frames. These three structures we use the stiffness matrix method of analysis and solve them. Okay, so here very fundamental in nature only, no great thinking is required for that. Then you have structural dynamics. In structural dynamics again, whatever we have learnt in first year engineering mechanics, the mechanical vibrations, their time period of vibration or the frequency, etc. There for a spring you have studied in first year, then now you will study it for the structures. That means instead of stiffness of a spring, you will take stiffness of a structure. In moment distribution method, you will know how to calculate stiffness of a beam or stiffness of a frame. So, using that stiffness coefficient, we will find what is the time period of vibration or the frequency of vibration, etc. So, simple questions will be asked in the dynamics part of it. In our analysis, structural analysis, these are the only topics available. Any question given must be within this only, and within a single day itself you can completely revise after understanding the basic concepts. Okay. So, having understood the bird's eye view of structural analysis, Now we'll take up the first topic, analysis of statically determinate trusses. Now we'll see the first topic, analysis of statically determinate trusses. First we'll see what is the meaning of a truss. Truss means is a structure where all members are subjected to axial forces only. That axial force can be compression or tension, no bending moment anywhere in the structure. As in strength of materials we have studied, such members where the members are subjected to only axial forces, you call it as a link. So in a truss, all members are called links. Such a link construction, we call it as a truss. It is a structure in which all members are subjected to axial forces only. That is tension and compression. Bending moment is zero. Zero everywhere in the structure. Bending moment is zero everywhere in the structure. Such structures we call it as a truss. Example. So this is a truss construction A, B, C, D, E. Let us say. Now you see all members must be straight and connected by smooth pins at the ends. Loads must be applied only at the joints, either vertical or horizontal, but they must be only at the joints. Then your link behavior will exist everywhere. So this is a truss. In a truss, all members are called links. When you are drawing in strength of materials the shear force and bending moment diagrams, a cantilever is attached to a simply supported beam with the help of a link, let us say. Link means both ends are pin connected, no intermediate loading. So that link will only transfer axial load in the form of a tension or compression. Such link construction we call it as a truss. So this is the definition for a link. Link means it is a structural member connected by smooth pins at the ends and not loaded at intermediate location. It should not be loaded at intermediate location and connected by pins. Such construction we call it as a link. In a structure, if you have only links, then we call it as a truss. Next, we will see this link can only take tension or compression. It cannot take bending moment. Why it cannot take bending moment? We will see with the help of free body diagrams in the later stages. First you understand that link means that. Next, second one is frame. Frame means again a structure where the members are subjected to bending moment also. In addition to tension and compression, there will exist bending moment also. Then we call it as a frame. If bending moment is 0, that frame becomes a truss, like that. Frame means it is a structure in which members are subjected to bending moment also. In addition to tension and compression. Supposing that same member you take, same structure you take it, now you have applied one load here, let us say some W1, then the other load you are applying on the member itself directly, let us say like this, BC member. Like this, if you apply load on the member itself, naturally it will bend. That's what in strength of materials you have studied. Once there exists a bending moment in any part of the structure, we cannot call it as a truss, it becomes a frame. Now this is a frame, maybe a pin jointed frame, okay, but frame it is. Member BC bends. That's why it is called a frame. Okay. Next, with this understanding, then when you want to, now we want to analyze such trusses. When you are analyzing the trusses, what are the assumptions? Are like this. Loads must be applied only at the joints, members must be straight. They must be straight, need not be prismatic. Prismatic means same cross section need not have. It can be varying cross section, but it must be straight. Finally, truss means a structure where there will not be any bending moment at all. Do whatever you want, but there is no bending moment, then it is called a truss. Now, let us see accordingly what are the assumptions involved in the analysis of trusses. That we will see in the third point. Assumptions in the analysis of trusses. We can also say assumptions means precautions. Precautions while building the truss is this one. First one is all members must be straight and connected by smooth pins at the ends. What happens if the members are not straight? See, otherwise, if the members are curved, then they will bend. They will bend and structure, and the structure cannot be called as a truss. What it means is, supposing that you are applying some load W1, W2 like this say A, B, C, D, E. This AB member is not a straight member, let us say. You are having a curved member like this. Assume that you have a curved member. AB is not a straight member, curved member. Then what happens if I take the component of some W1, if it acts in this line, this much eccentricity is there, this the cross section is here, line of action of the force is here. This is your eccentricity. So force is acting in this line, cross section is somewhere here, then line of action of the force into perpendicular distance, then that much bending moment will be there, force into perpendicular distance. So there is, if you have a straight member, apply compression, it will only be under compression. If you take a curved member and apply compression, say your line of action of the force is here, you have a curved member, but cross section is here, so force into perpendicular distance, it will produce some moment. So once there exists bending moment, then you cannot call it as a truss. Now because of that, it becomes a frame. So this is not a truss. Why not a truss? Curved member AB bends and must be straight, that's all, need not be prismatic. That means if you see airports, if you see trusses, sometimes 10 meters length also truss members will be there. There the pipes, they are tapered pipes, two tapered pipes we attach it and we get a very long member. Those members, AB member should be straight but need not be prismatic. What it means is, as you can build a member like this. This is a member AB, let us say, and you are applying compressive force. P here, some force whatever you are applying. There is no bending moment in this member. You see, the member AB is straight but not a prismatic one, still acceptable. Such type of things we use where you want to prevent buckling, say. Here more cross section will be, the diameter will be more, here diameter will be less. So to prevent buckling, we use this type of members. So tapered section. Member must be straight, but so such members we can use, but need not be prismatic. What is the meaning of prismatic? Having same cross section throughout the length. Having same cross section throughout its length. Such members we call them as prismatic members. So, but the members must be straight, but they need not be prismatic. That is the first thing. But they must be pin connected. They should not be curved members. Now the second assumption or second precaution is loads must be applied only at the joints. What happens otherwise? Otherwise, if the loads are applied at intermediate locations, they will bend. And the structure cannot be called as a truss. Again, meaning is this one. You must apply loads only at the joints. Now, if at all you apply load here, say, then it will bend. So, this becomes a frame, not a truss, we can say. It's not a truss because member BC bends. BC bends because of intermediate location of loading point. So, there should not be any intermediate location loading. Loads must be only at the joints. So, accordingly, when you are constructing the trusses and when you are having, say, roof covering material, you will ensure that the purlins we place only at the truss joints. On the purlins only roofing material will rest, so that purlins will take the load and transfer to the truss joints only. Even in the truss bridges also, nowhere the trains, when they are moving on the bridges, they are in touch with the truss members. Entire trains, railway track and the cross girders and stringer beams, everything they will rest on the truss joints only. On the truss joints, cross girders will be there, and only at the cross girders, only at the truss joints, nowhere else. So, cross beams will be there, cross girders we can call it, and entire bridge, that means the railway track, sleepers and trains, everything they move on the cross girders only. So, cross girders take the load and transfer only to the truss joints. So, we ensure that in the truss construction, whatever load you apply, it will pass through the joint only, not on the member. So, such precautions when you take it, such assumptions, with those assumptions, assuming that you are applying loads only at the joint, some precaution you have to take it so that it will pass through the joint only. And all members we ensure that they are straight but need not be prismatic. Now, with this assumptions, we analyze the trusses. Now, you see, in a truss, the number of members, joints are having a definite relationship. We'll see what it is. This is a link construction, as I told you. Such link construction is stable only when it is in the triangulated form. If you have a square or a rectangle form, let us say, then that is not a stable form. Means without developing any stresses, it will undergo rigid body translation or rigid body rotation. Any structure which undergoes rigid body translation or rigid body rotation is called unstable or mechanism. See this fourth point. Why we are having all triangles is this is the reason. Only then it will be stable. Now you see, assume that why triangles, why not squares? This is one link construction say. Now this is a mechanism, means this is unstable structure. Unstable means that rigid body translation. Now you see this structure, if you hold here and tap like that, simply it will move and fall down, or push it like this, it cannot take. Supposing that here you are holding at these two locations, push it, freely it will move. It will move like this will come down. So just tap like this, it will translate and it will fall down. Supposing that if now push it easily, it can go this way. So easily it can take this shape, or because it is taking like this, it will come down. Like this it can take up, just push it, it will come down. To facilitate this rotation, it will come down. So it will take this position. So that means it is a mechanism. Mechanism means the structure is unstable. Supposing that if you make a triangulation form, same structure, instead of having in the rectangular form, you add one member like this say. Now if you push it, if I push it like this, see here in this case, original length is this much, diagonal length. After it has taken, because there is no member, easily it will, this increases. Compared to this length is more. But since no member is there, freely the joint translates. But in this case, to increase like this much length, it has to be pulled. In SM, you have studied that pure shear case. If at all one element is subjected to pure shear, one diagonal is under tension, another diagonal is under compression. So there is a member here, this under tension. If at all another member is there, that will be under compression. So in this case, because of this member, it is under tension. When you push it, your push will be resisted by this member by undergoing tension. That means it cannot translate, or this joint cannot translate without developing stress in this member. That means if any member translates or rotates after developing stress, then they are called deformations. So it is stable structure. Without developing deformation, just push it like this, if it moves, then it is mechanism. So such type of triangulations are stable forms. So for horizontal, vertical loads, in plane horizontal, vertical loads, they are effective. They can take the loads and they deform. Compressive stress, tensile stress will develop, and such structures are stable structures. Since simple trusses are built by taking this one, a triangulated form we will make it. Okay. So accordingly, to make a triangulated truss, there is a relationship between the number of members and the number of joints. So that point we will take in the fourth concept. In a truss, the total number of members and the total number of joints are related by m is equal to 2j minus 3. This is what we have learnt in your first year engineering mechanics, strength of materials also, m is equal to 2j minus 3. Then what is that 3? That 3 does not stand for number of equations of equilibrium, that 3 comes from this one. Assume that you want to build one truss. First one is, for the first 3 joints, number of members are 3. for the first three joints, three members are required. Now such panels, we call them as panels. We want to build, if you have a very long truss, let us say, such type of triangulated construction we extend. Okay, so now we want to build one more panel, let us say. Then what will happen? For this joint, two members are required. One more I want, let us say, another two members. Such construction we call it as simple truss construction. So, what does that mean now? For this joint two members, for this joint two members. That means for each additional joint we require two members. So, for each additional joint, two members are required. Now, these two statements, if you represent it mathematically, it becomes like this. First, we will see the blue color and red color members. So, M is equal to 2J. If you have say two joints, first three joints you remove, we will see that point later. These two joints means four members. That means number of joints are 2 say, members are 4, so 2J. So, M is equal to 2J is satisfied from this second statement. But this I want to apply to the first statement also. First three joints, three members only are required. But as per this one, how much? First three joints only, J if I put 3, 2 into 3, 6 you will get. But we have only 3 members. So, instead of 6, 3 members only are there. So, subtract that 3. Now, this equation is useful for this first 3 joints also. That 3 comes from that. For each additional joint, you require 2 members except for the first 3. For the first 3 joints, instead of 6 members, you are having only 3 members. So, that 3 you subtract, 2 into 3 means 6, 6 minus 3, 3. So, now equation tallies, 2 statements are satisfied with this mathematical statement. Okay. This truss construction, now if you want to keep it on 2 supports, then we call it as a simply supported statically determinate truss. So, if this condition is satisfied, you will get a statically determinate, a triangulated truss. Triangulated stable truss you will get. Okay. If the above condition is satisfied, we get a stable triangulated and determinate truss. Stable triangulated determinate truss. Okay. Now, having understood this one, how the members and joints are related, now we will see the analysis. If at all, coming to the fifth point, if at all you match number of members are exactly equal to 2J minus 3 say, then we call it as a perfect and stable truss. If M is exactly equal to 2J minus 3, we call it as perfect stable truss. Even if one member is missing, supposing that in this triangulated form, Even if one member misses out, it will collapse. Collapse means rigid body translation, simply it will become unstable. So, if number of members are less than 2j minus 3, we call it as deficient. Deficient or unstable truss. Thus, this becomes unstable. If you provide more members than 2j minus 3, that means number of members are greater than 2j minus 3, we call it as redundant. Redundant or indeterminate truss. Indeterminate truss internally. Internally means within the structure it is indeterminate. Means equations of equilibrium you cannot use to find all member forces. But the point is already this structure is stable. Stable, and why should we provide more than 2j minus 3 and waste our money? Supposing that why we provide more members than 2j minus 3 is this one. You have built one structure, simple supported, big structure you have built. Assume that this member was under compression, and due to some unforeseen reasons, force extra came than what you have expected. So, because of that additional force, that member buckles, let us say. If one member fails this mechanism, that means triangulation gone. So, this will collapse. Entire structure will fail because of one member. Such cases, if there is a possibility of failure of one member, then to protect the entire structure, we add one more member here like this. This is one additional member. Okay. In case this member fails, this member will take care of the stability of the structure. If this fails by compression, this will be under tension and it will remain in position. Such additional members which we provide more than 2j minus 3, they are called counter bracing. Okay. So, these counter bracing members provide more stability to the structure. In case one member fails, that counter bracing member will take care of the stability. So, indeterminate stress. If m is greater than 2j minus 3, it is indeterminate stress. Why we provide is, we provide more members than 2j minus 3 to make the structure more stable. These additional members are called counter bracing. You will see in later how one member fails by compression, another member will be under tension, and how the stability will be restored. That with the help of free body diagram I will explain. In the end of this method of joints or sections are over, we will see how counter bracing members act. Okay. So, this is about the trusses. Introduction to a truss. Introduction means what is a truss, what is a classification, stable or unstable or indeterminate truss. Now, let us see how a numerical can come on the meaning of a truss. Now on the fundamentals, how the questions can be asked is like this. For the structure shown in figure, bending moment exists in the member in one of the GATE papers. They have asked this as a 2 marks question. In the member AB, in the member AC, both AB and AC, no member. Now you see, if a structure like this is given, here there are 2 members, all members are straight, connected by smooth pins, load is applied only at the ends, at the joints. Actually, if they show like this, it is a wall. It may be a wall, let us say. Okay. In the wall, this whenever you put a circle, that means there must be a pin there, or there is a bolt you visualize. So in the wall, you chip off some area and put one bolt like this, and you chip off area and put one bolt here and fix it both ends. Now there is a gap here, insert one member. This member, AB member, has holes at both ends. So first you insert that member at B, and after inserting it, this is now fixed in the wall. Let us say this member now horizontal, this one member horizontally it goes. There is a hole in this member, and one more member will come and you overlap it. One horizontal member is like this, one inclined member was there like this. When you superimpose, you overlap 2 members, now take a drill bit, make a hole into the 2 fingers and insert one bolt or pin. That type of connection will be there. That bolt is sufficiently long. One member this way, another member this way, in between the 2 members there is a small gap. So pin is there. On the pin only you will hang the load. That load, whatever you are hanging, is not in contact with AB or AC. That means pin is so sufficiently long. So you will hang the load on the pin, let us say. You visualize that way. Then what will happen? That pin will take the load and transfer to these 2 members in the form of tension or compression only. This cannot bend. They cannot bend. They cannot take shear force or bending moment because of the pin conditions. We will see with the help of free body diagram what makes this that it cannot be able to take the shear force or bending moment. Okay. Since all conditions are satisfied, now you understood how the construction is. Whenever you put a circle means there is a pin, and to that we hang the load. To the pin we are attaching the 2 members. They are separated. First one pin, another one pin is there, one member will insert, another member will insert from this side. So member is pin is so sufficiently long and 2 members will span this way. Such construction only, if it is there, that is called a truss. Since all members are straight, connected by pins, here also circles are there, that means in the wall there are 2 pins. So those pins cannot move up or down. Horizontally also they cannot move, they are fixed in position. But that member, because you are hanging it loosely, they can rotate. That is called pin connection. Okay. So since all conditions are satisfied, load is applied at the joint, means load is applied on the pin, members are straight, no intermediate location. Now all the members behave like links, that means they will not bend, no member bends. So this is the explanation. All members are straight, pin connected and loads are applied at the joints. So each member behaves like a link. So no member bends. Okay. It looks as if to the member AB this load is applied perpendicular, so there will be a bending moment. But this load is not applied on the member AB. It is applied on the pin. There is a gap between the member AB, load and the member AC. So on the pin, one member goes this side, another member may go this side, and between them you will hang the load. That's how the loads are applied at the joint. Loads are applied on the pin means that. Okay. Now this is a one question. Once they have asked which member bends, so you must see how the structure is. Is it a truss or not? First you have to observe how the connection is made. Accordingly you have to analyze. Next one is the truss shown in figure is. Like this you could say, this is perfect, deficient, redundant, say none. Now you have to count here the number of joints 1, 2, 3, 4. Now see this member and this member, circle was not there. If there is no circle, it means that those two members, one member is going like this, another member going in the perpendicular direction. If you see from the side, there is some gap between the two members. They are not at all touching each other. But if you put a circle, then four members are bolted at that point. That's the meaning of that. Circle is not there means these two are separate, independent diagonals. At this point, there is no contact also. Now, total number of joints are 4. This is what you have to analyze. Number of members 1, 2, 3, 4, 5, 6 members. Now you see M and 2j minus 3 if you see how the relation is. Number of members are 6. 2 into 4 minus 3. So 6 is greater than 5. So M is greater than 2j minus 3 it became. So redundant. Now how many members are there in excess of 2j minus 3? 6 minus 5, 1. That means there is one counter bracing member. Redundant. There is one counter bracing member. Then which member behaves like a counter bracing? Depends on the type of loading. If a load comes like this will be under compression, this will be under tension. If this collapses, then this becomes now counter bracing. Now if force is applied this way, let us say, if this fails, then this will act as a counter bracing. One is like a will act as a counter bracing if the other member fails, like that. So this is only counter bracing, this only counter bracing, we cannot tell. It depends on which direction the load is coming, which member fails. If one member fails, other will take care of the stability of the structure, and whatever forces are there, that member, the remaining one member is capable of taking the loads. Tension member capacity is always a member, same cross section is there, say, its compression carrying capacity, tension carrying capacity is totally different. Compression carrying capacity is limited by its buckling nature. Tension, no question of buckling. At least 2 to 3 times more load they can take under tension. So if one member fails by compression, other member will take care of the forces also, entire force developed, or once this is removed, the loss of this member, whatever additional force that may come, because the other member is under tension, it can take those additional forces easily. So that is the meaning of counter bracing. If one member fails because of the compression, other will take care of the triangulated form. So that no rigid body translation or rotation can take place. So on the introduction to trusses, these are the questions that they can ask. Now let us see how to analyze the trusses. Okay, now we will see the analysis of trusses. We have two methods to analyze them. Method of joints, method of sections. Actually, method of joints is a special case of method of sections. It is a special case of method of sections only. Now first we will take up the method of joints. Why it is a special case of method of sections is, method of joints we will take equilibrium of a joint, and that means joint equilibrium we take it and find forces in the members. And when you are taking equilibrium of a joint, all members meet at one point. So you cut, method of sections, what we do is we will cut the member so that a section of a truss equilibrium we will take it. Equilibrium of a section of a truss we will take it, that is why it is called method of sections. So sections or joints, both the methods cutting is necessary. Depending on how you cut the members, you call it as method of joints or method of sections. You cut the members such that all the members are meeting at one point, then that analysis we call it as method of joints. If all the cut members they don't meet at one point, then it becomes method of sections. There is a difference depending on how you cut, method of joints and method of sections. So now we will discuss in detail about method of joints and sections. First we will see the method of joints. First point is equilibrium of a joint is considered in method of joints. Second one, how to do that? Procedure. It is a two-step procedure. Each step takes around 10 seconds time. Within say 20 seconds or maximum of 30 seconds time, you can complete any question on method of joints problem. So first step, find support reactions. Considering equilibrium of entire structure. In SM engineering mechanics, you know, you have already done how to find the reactions. Generally, the reactions, when you are finding it, by inspection itself, you will be able to find the reactions. If the structure and loading are symmetrical, then supports share the load equally. Okay, now whether the support is like that, by inspection means I think already you have learned, you have a simply supported beam, say central point load. Support is symmetrical and loading is symmetrical, then two supports will share the load equally. So, such cases W by 2, W by 2 we know like that. So, by inspection itself you can find what the reactions are. Say it takes 5 seconds to 10 seconds time. Then second step, consider equilibrium of a joint where only two members are meeting, or where only two unknown forces are available, and use sigma x is equal to 0 and sigma y is equal to 0 to find them. Now, the point is, why should we take a equilibrium of a joint where only two unknown forces are available? To find and proceed to other joints. Proceed to the other joints in the same way. Okay, now point is, why should we take only a joint where only two unknown forces are available? Now, you see, this is what you have learnt in your engineering mechanics. Assume that at a joint, so many members are meeting, forces are meeting. This can be members or forces, whatever way you want to call it, A, B, C, D, E, let us say. This is force in the member AB, FAB, force in the member AC, force in the member AD, AE. Member or some forces are acting, let us say, so four forces are there. Now, we know x axis, y axis when you take it. Summation of x components of all forces is equal to 0. I can write one equation. FAC cos theta, FAD cos theta, or FAE sin theta, AB sin theta, or AB cos theta, depending on which axis the angle theta is given. So, summation of x components of all forces is equal to 0. It has to be 0, otherwise it will not be in equilibrium. Then sigma y is equal to 0, I can take it. Y components of all forces minus FAC sin theta plus FAD sin theta. All such y components of forces must be 0. Then if I take moments of all force about A, what I will get? FAD will give 0 moment, this will give 0 moment, this will give, all will give 0 moment. So you will get 0 is equal to 0. If you write sigma MA is equal to 0, what you will get is 0 is equal to 0. With 0 is equal to 0, what you can find? So this sigma MA is equal to 0 becomes a useless equation. So this system of forces are, these are all in the same plane meeting at one point. It is a coplanar concurrent force system. Coplanar means lying in the same plane. Coplanar and concurrent force system. So, in a coplanar concurrent force system, number of useful equations of equilibrium are only 2. In one of the papers, they asked that itself as a 2 marks question. In a coplanar concurrent force system, equations of equilibrium available are 1, 2, 3, 4 like that. You should answer 2 but not 3. Third one is this one. 0 is equal to 0 is useless. So, we can write in a coplanar concurrent force system, the number of equilibrium equations available are only 2. With 2 equations, we can only find 2 unknowns. We can only find 2 unknowns. That means you must select a joint where only 2 unknowns are there. Only then you can use method of joints. So, we must select a joint where only 2 unknown forces are available. That is the explanation for that. Okay. So, now you understood why we should take only should take a joint where only 2 unknown forces are there. If all joints have minimum of 3 forces, say, then we cannot use method of joints. You must take some other concept to find the member forces. We will see one by one how we should manage the member forces. Okay. Now, in the process of finding the member forces, how you have to detect whether a member force is compressive or tensile. Now, these observations are required. This I remove now. Okay, now let us see note 1. Assume that we have taken one member, you pluck out one member inclusive of the pins from a truss. Now that is now looking like this. This is one such member, let us say. There is a pin here. So member has holes, and in the holes there are pins. On the pin only we apply forces with the help of other members. Assume that all other there are 3 members are there attached here. Here 4 members are attached, say. Those 3 members put together are pulling the pin with a force of P, let us say. And here also all 4 members, whatever 4 or 5 members, they must pull this pin with a force of P. Otherwise, this will not be in equilibrium. Now we have two pins here in this direction, one member. Now I want to draw free body diagram of a pin. This is the free body diagram of pin. Pin or bolt, whatever way you want to take it. We have such a long bolt. Long bolt was there. All members put together are pulling with a force P, say, on the pin. So free body diagram of a pin means on the pin what others are doing you have to show. That is called free body diagram. So what are the 3 members or 4 members they are doing is, they are pulling the pin P with a force P, let us say. Now to balance this force P, this member will exert some force on the pin, and that force must be P. This P is the force exerted by this member on the pin. This P is the force exerted by all other members. This is now called free body diagram of bolt. First year engineering mechanics you have studied what is the meaning of free body diagram. Free body diagram means it is the diagram of a body on which what others are doing you have to show. Now that is what we have shown. Now we want to draw free body diagram of the member. So when you draw the free body diagram of the member, on the member what the pins are doing you have to show. This pin is pulling this member with this much force P. So if member is pulling this pin with a force P, in return this pin will pull this member with a force P. So cut here, cut here. Now to balance this P, at this point this pin must pull him with a force P. Otherwise member will not be in equilibrium. Now this force is exerted by the pin. If I draw the free body diagram of the pin, on the pin what member will do is will exert a force P like this. To balance this P, the all other 3 or 4 members will pull him like this. Now individually each member is in equilibrium. Remember one thing, that in a structure, if a big structure is in equilibrium, let us say, any small piece you pluck out of it, individually each member must be in, or each piece of the structure must be in equilibrium like this. So now this free body diagram tells you this one thing. This is the pin, these are the arrow marks. If the arrow marks are away from the joint or away from the pin, it means that force in the member is tensile. See, it is getting pulled. SM you have studied that point. If any member is subjected to 2 pulls, it is called tension. If only one pull is there, other pull is absent, let us say, then that is not called a tension, simply rigid body it will translate. For any member to be under tension, 2 pulls must be there. For any member to be under compression, 2 pushes must be there. Any member to be subjected to bending moment, 2 movements must be there. If only one movement is acting, as a rigid body it will rotate. Another movement must be there. If at all you have applying clockwise, here anti-clockwise should be there, then only it will bend. For a member to bend, you require 2 movements. For any member to get twisted, you require 2 movements. If only one movement is acting on a member, then as a rigid body it will rotate. Another movement is required for that to get twisted. So for tension, compression, movement, bending or twisting, you require 2 forces. So it is now under tension. So this is, now this free body diagram tells you that if the arrow marks are away from the joint, it means that force in the member is tensile. That is the first conclusion. If arrow mark is away from the joint, it means that force in the member is tensile. Second point. Same thing we can write. Supposing that you have a member inclusive of pin you have taken and it is subjected to forces like this, say P. Then as in this case, if you draw free body diagram of the pin and members, it looks now like this. This is the pin, let us say. Same thing I will write P here, P here. This member free body is like this. P here, P here. The same way, instead of arrow mark away, now it is towards. Now you see this pin free body diagram, if you take it, either external force or this internal resisting force, if arrow marks are towards the joint or towards the bolt, it means that force in the member is compressive. If arrow mark is towards the joint, it means that force in the member is compressive. This is the second observation. Then third point is this one. Assume that at a joint, three members are meeting. That means in a big truss, we have taken a joint, you pluck it out inclusive of the members, and those three members happen to be like this, say. No external load here, only three members are acting, are configured this way. Now force in the member AD, let us say FAD. Force in the member AB, let us say FAB. Force in the member AC, let us say FAC. So there are three forces meeting at a point, three concurrent forces meeting at a point. For them to be in equilibrium, one of the forces has to be zero because no external force is acting. This is, say, x-axis. You don't want, you can take it as y-axis also. This is, say, y-axis, this is theta. Because the truss is in equilibrium, this joint also must be in equilibrium. Now sigma x0, we can make it. Component of a force means what? Component of a force in first year engineering mechanics we have studied the effect of the force in that particular direction. So if a force is acting like this, what is the effect of that force in the other direction, say? That means the component we are finding. So we also have learned that any force cannot have a component in its perpendicular direction. That means that force has no influence in the perpendicular direction. Rotational effect will be there, but direct action will not be there. So if I take here sigma y0, any force acting along positive y-axis positive, any force acting along negative y-axis we take it as negative. I will take this as positive y-axis. FAD and y-axis, FAD and FAB, they are collinear. So at a joint, three forces are acting, out of them two are collinear. See, collinear means same line of action. So two forces are collinear. Now force in the third member has no choice, it has to be 0. Now let us see why it should be 0. FAD has no influence in the y-axis because 90-degree angle. The theta in this case about the from x-axis and FAD, theta is 0. Y component means what? FAD sin 0 is 0. So it doesn't have any y component. Effect of force in the y direction is nil. Here also same thing. So only one force is acting. So plus FAC into, this FAC is acting like this, its y component is FAC into sin theta. So, this component you will get it, FAC sin theta means this component. So, plus FAC into sin theta must be 0, only one force is there. Sin theta can't be 0 because some fixed angle is there. Now, who should be 0? FAC only should be 0. So, what you can conclude? At a joint, if three forces are meeting, out of three forces, two are collinear, no external load here, then force in the third member is always 0. So, at a joint, if three members or forces, whatever it is, 4 members or forces, same only, 3 members or forces are meeting, two members are collinear, then force in the third member is always 0. If there is no external load, at that joint, like that. Now, another conclusion we can make it, why we should, we have to write in the form of a note is, if you understand why FAC is 0, under what circumstances force in the member can be 0 if you understand, in the exam we cannot afford to write this and tell that FAC is 0, that much time you will not have. By inspection itself we should be able to tell whether the member force is 0 or not. By inspection itself 1, 2, 3 members, 2 are collinear, third has to be 0. It should take only 5 seconds time, we should not write so much and again write that. So, that is why we have written it as a conclusion. So, this member force has no choice, it has to be 0. Then why should we keep that member? If at all any external load is acting, then that member AC will take. If no external load is there, then only it will be 0. We will see later why, if the member force is 0 also, why should we keep such members? The reasons we will see again in the next example problems. Okay. So, now we will see note 4. Instead of 3 members, let us see only 2 members. Okay. Fourth observation is this. Assume that at a joint 2 members are meeting. This is 2 non-collinear members, means they are not acting along the same line. They need not be perpendicular, they can be inclined also like this. See, they are not collinear, same line of action is not there. This is also 2 non-collinear members. As a last case, we will take 2 collinear members. This point let us say A, B, C, FAB, FAC. This is 2 collinear members. Okay, now let us see first this one. This point let us say A, B, C. Force in this member, let us say is acting like this, FAB. FAC. Now, this is the case. At a joint, two members are meeting which are not collinear, means not same line, some other line. In this case, 90 degrees angle, and no external load here. Such cases, if I write now sigma x is equal to 0, what happens? If you write now sigma x is equal to 0, summation of x components of all forces is equal to 0. Any force that is acting right side positive, any force that is acting left side, you take it as negative. This is plus FAB, and this AC member does not have x component because 90 degree angle problem. So only FAB, now it has to be 0. That means FAB has to be 0, otherwise joint will not be in equilibrium. Now you write sigma y is equal to 0. Upward force is positive, downward force is negative. Now this FAB doesn't have y component, only FAC, and that force has to be 0. That means at a joint, if two non-collinear members are meeting with no external load at that joint, forces in both members have to be 0. Now let us see 90 degree angle is not there. This point let us say A, this force let us say FAB, this let us say FAC, this member B is C, this is some angle theta let us say. Two members are meeting, but angle between them is not 90 degrees, some other angle, but no external load. Now let us see, this is your x-axis, this is say y-axis. Okay, first we will write sigma y is equal to 0. Upward positive, downward negative. FAB is acting along x-axis and it doesn't have y component. That means FAB will not influence sigma y is equal to 0 equation. So FAC is sin theta. FAC is sin theta, only one member is there y component and it should be 0. That means FAC has to be 0. Sin theta can't be 0. Now you are ready to use sigma x 0. Once this is 0, I can now write sigma x 0. I will find that this member is not there, so cut, remove it off, only one member. This is FAB has to be 0. So you will find that whether angle between the two members is 90 degrees or not, forces in both members have to be 0, otherwise joint will not be in equilibrium. This observation will help us in choosing which members have 0 forces quickly. Last case you see two collinear members are there. If I take here sigma x is equal to 0, right side force is positive, left side force is negative. This you can write plus FAB minus FAC must be equal to 0. So you can at the most tell that FAB is equal to FAC. That's all. Individually, they need not be 0, they are equal. But if FAB is 0, FAC will be 0, but if FAB is 20 kilonewton, that will be 20. They can be 0, but they need not be 0 also. 20 means 20, 30 means 30 will be there. But in these two cases, they have to be 0 only. So your conclusion is, at a joint, if two non-collinear members are meeting with no external load, forces in both members have to be 0. That we write conclusion. At a joint, if two non-collinear members are meeting with no external load, at that joint, forces in both members will be 0. So, With this 4 points, now we will try to solve the numericals. Now let us see the numericals. Force in the member BD. We have a truss. This point, let us say A, B, C and D. Assume that you have applied a load of say 10 kilonewton. Okay. Now, we cannot take the free body diagram of joint B to find force in the member BD. Why we cannot take? I told you earlier that at a joint, when you want to use method of joint, there must be only 2 unknown forces. If 3 unknown forces are there with 2 equations of equilibrium, you cannot find 3 unknowns. So, B you cannot use it. D we can use it, you see. At D, supposing that this 10 kilonewton, instead of keeping it here, assume that I have kept 10 kilonewton here, say that after that we will see here also. Okay. Now, we can, to find force in the member BD, we cannot take joint B. It looks as if entire 10 kilonewton BD member is taking. For, I told you, for any member to be under compression, you require 2 forces. With a single force, you cannot keep a member in compression. It will, as a rigid body, it will translate. So, free body diagram of joint B you cannot take to find FBD because 3 member forces are unknowns. You have only 2 equations of equilibrium, sigma x0, sigma y0. So, that is ruled out, but D we can take it. At D you see 3 members are there, 1, 2, 3 members, 2 are in line, so third has to be 0. When I am looking into this joint configuration, how much force at far end is there, we do not have to worry at all. Method of joints, that is the thing. Now you see, you visualize it like this. Because the truss is in equilibrium, any small piece you pluck out of it, it should be in equilibrium. Take scissors, cut here, cut here, cut here, like this. Cut it like this, pluck it out, stick it here. This is how it looks like. This is the free body diagram of joint D. Inclusive of the members. Assume that force in the member BD is acting like this. This force in the member CD. This is force in the member AD. So, on the pin, there are 3 forces, one force like this, one force like this, another force. If FPD is 1 Newton, let us say, to balance this 1 Newton below the pin, nothing is there. Because of that 1 Newton, what will happen to the pin? It will go up. As rigid body, it will translate because nobody is there to pull him down. which means that FBD has no choice. Force in the member BD, it has to be 0. Otherwise, pin will not be in equilibrium. If I write now sigma y is equal to 0, FBD has to be 0. Now you see, when I am taking this free body diagram, at the far end, whether 10 is there, 1000 is there, will not come into picture at all. So whatever may be the force here, 10 kilonewton or 1000 kilonewton, BD member says, I resign. I cannot take any load. Why it says it cannot take any load is because of the configuration at D. For that member to be under compression, there must be someone to push him up. Nobody is there. So with single force, you cannot keep it in compression. It is like a cantilever portion. One end only you apply some load, other end load is not there. So it cannot be subjected to compression. So force in the member BD is 0. If force in the member BD is 0, these are generally in the steel structures we study again. These members can be channel sections or angles, I sections, like different standard steel sections are there, we use them. This means there is a force in the member is 0, but you are putting one angle section or channel section, say. So much of money is wasted because force is not there, but still we have to use it. See, for this loading only, force in the member BD is 0. If after some time some other load comes here, say, then this member only should take. So just because force in the member BD is 0 for a particular loading, it does not mean that it is a waste member. It is, for some other loading, it only has to resist. For example, this is the slab where we are sitting like this, say, and we are here between say 10 to 5. At 5:30 we will come and observe here nobody is there, entire hall is empty. So we cut the entire slab, say, because nobody is there, why to waste the slab? You cut it and use it for some other purpose. Then tomorrow morning when you come here, where will we sit? Already you have removed it. So again, that means for a particular period of time, force on this member may be 0, but that does not mean that it is a waste member. Some other time, some other forces may come, in such cases that only should take. Here also same way. For this loading only it is 0, for some other loading it will take the load. Maybe wind load is acting, say. Then this member BD will resist that load. Okay. Now let us see that problem. Supposing that if you have force in the member BD, if I show it like this, say, this I remove now. Next question is force in the member BD. Assume that we have a same truss. After some time, there is a load of 10 kilonewton coming here. Now what is the force in the member BD? Now you see, again to find force in the member BD, joint B equilibrium we cannot take it because 3 unknowns are there, we have only 2 equations of equilibrium. So you have to take joint D. 1, 2, 3 members are there, 2 are collinear, third will be 0 if there is no external load, but load is there, which means that BD will not be 0. So 10 down, to balance this 10 kilonewton is acting on the pin. Pin is getting pulled with a force of 10, then who should stop it? Member. So member will exert a force of 10 kilonewton on the pin, then pin will be in equilibrium. If here arrow mark is away from the joint, far end also arrow mark must be away from the joint, because one member, one force only is possible. Now you see, it looks FBD how much? Force in the member BD. It looks as if the member BD is subjected to compression of 10. But these two blue color arrows are not acting on the member BD. They are acting on the joint. In any textbook, when you see the arrow marks like this, those are the arrows acting on the pins, not on the members. So, as I told you in the note 1, if arrow mark is away from the pin or bolt, it means that force in the member is tensile. So, FBD is, force in the member BD is 10 kilonewton tensile. Then if, what is the force in the member BD if you want to find, you have to draw free body diagram of BD separately. Then supposing that if this free body diagram, if I draw one by one, it looks now something like this. This is 10 kilonewton down. This is joint D. Force in the member, some arrow marks are there, let us say. Force in the member CD, force in the member AD. This is free body diagram of joint D or bolt at D. Joint D or bolt at D mean the same. So, to balance this 10 down, the member might have exerted a force of 10. Otherwise, that pin will not be in equilibrium. Now, you see, if I draw free body diagram of the member BD, it looks now like this. BD. Now, when I draw free body diagram of BD, on BD member, what a pin is doing, you have to show. So, this pin now is pulling him down with a force of 10. To balance this 10, another 10 should be here. This is your free body diagram of member A, BD. Now, if I take the free body diagram of joint at B, this one, this 10 is acting up means who will give this 10 up? Pin only should give. So, when I draw free body diagram of the pin at B, the force will act vertically down, 10 down. This is B. This is free body diagram of bolt at B. Now, to balance this downward force, who will stop it? These two members. There are two members, they will exert an upward force like this on the pin. This is maybe FAB, this is FBC. The resultant of these two black color forces is vertically up, magnitude is 10. So, 10 up, this 10 down. So, this joint B is in equilibrium. Now, you will find that each component is in equilibrium. This is what I have shown in the note 1. Free body diagram of the joint without these two members. I have done only this line. Pin, arrow marks away, away. These two are away. So, this is how the force flows from lower joint to the top joint. So, when you are drawing the free body diagrams, one below the other like this only you have to draw, then you will understand that how this 10 kilonewton is transferred to the joint B. Okay. So, this free body diagram tells you that it is 10 kilonewton tension. But in the exam, so much we cannot draw. By seeing this arrow marks, that is what note 1 I told you. If arrow marks are away from the joint like this, it means that force in the member is tensile. Force in the member is tensile, like that. Okay, next question. So, this how much it takes? Hardly 10 seconds to detect what is the force in the member. That is, to detect it as 0, 1, 2, 3, 2 are in line, third must be 0, 10 seconds. Now, let us see force in the member BC. This, let us say 10 kilonewton. This point say A, B, C, D. This length, let us say 2 meters. This is also 2 meters. We want to find force in the member BC. Now, here also we cannot take free body diagram of joint B to find BC because 3 unknowns are there. We cannot find because 3 equations of equilibrium. So don't take this one. Other end you see. At CC, you can cut it like this. That's the meaning of free body of this joint. So if I cut this way, because it is in equilibrium, any small piece you pluck out of it, it should be in equilibrium. So take scissors, cut here, pluck it out. In its isolation, it should be in equilibrium. Otherwise, the structure will not be in equilibrium. See here, this is what I have told you in the note 4. This force some FCB you take it. This force FCD you take it, say. This is free body diagram of joint C. Now apply sigma x is equal to 0. Force in the member CB or BC. Any which way we can write 0. If you write sigma y 0, FCD also will become 0. That means it looks as if this slope is also, let us say, 45 degrees. Naturally, this is also 45 degrees to 2 meters. Let us say like this. Okay. Now, at this joint, 2 non-collinear members are meeting with no external load at this joint. Other end there may be 10 or 1000, it has no influence on this joint configuration. So, 2 non-collinear members, no external load. So, for the structure to be in equilibrium, both members have to be 0. Otherwise, it will not be in equilibrium like this. So, having found that this is 0, this is 0. Now, let us see this member. If at all any member force becomes 0, let us say, you visualize as if 0, 0, right? Cut it, throw this piece out. Now this you have. At B now 3 forces are meeting, either 3 forces or 3 members, whatever it is. 10 kilonewton you can visualize as if that is a member whose force in that member is say 10. Otherwise, someone should give that load. So 1, 2, 3. These 2 are in line. Third now has to be 0. 1, 2, 3. 2 are in line, third must be 0 because already 0 you remove it off. So this value has to be 0. Then who will take 10? This member. Like this. This is towards joint. To keep this arrow in equilibrium, it has to be like this. Now 10 towards, so it has no choice. 10 towards only should be there. Now this free body diagram tells you that force in the member BD has to be 10 kilonewton compression. So force in the member BC 0. Force in the member CD 0, force in the member AB is also 0 because of 3 members, 2 are collinear, third has to be 0. Then force in the member BD, 10 kilonewton compression. Like this. See, by inspection we are getting. Supposing that this idea we didn't get, we want to find first the reactions and solve the problem, let us say. That also can be done. Now, same problem we want to solve it by taking the support reactions, let us say. This is A, B, C, D, 2 meters, 2 meters. Now, we will see how to find the support reactions. This is hinge support. At a hinge support, you have two reactions, VA, this is a HA, this is a VD. Hinge will give two reactions, roller support will give only one reaction. Okay. Now, from the equilibrium of the entire structure, you have to see like this. Strength of materials, you have calculated many support reactions calculation problems, but in the exam, by inspection you have to manage, you should not write the equation and waste the time. Now you see 10 is acting like this, 10 cos 45, now we are not cutting any member, entire structure equilibrium we are taking. 10 cos 45 is going right side. To balance that, it should act left side. So 10 cos 45 means what? 10 by root 2. So HA 10 by root 2, directly we can write it. We should not write sigma x0 and waste time there. Then VA you want to find. Take moments of, you cannot write sigma y is equal to 0 because VA plus VD minus 10 sin 45 you have to write, and two unknowns will come, one equation. You cannot get any result out of it. Once you are writing one equation means one unknown, you should plug it out. So instead of sigma y 0, we will take sigma m 0. Take moments of all force about D equal to 0. HA is passing through D. Line of action of HA is passing through D. So HA will give 0 moment. Now VA, travel from tail to the head towards D like this. Once you are moving from tail to the head like this, you have to see where point D is. D is here. So you must shoot yourselves towards the D like this. So clockwise movement. You should not move like this away and say that anti-clockwise. When D is there, when you are moving this way, you should not go away again, come back there and say anti-clockwise. You should directly move towards point D to detect whether it is a clockwise or anti-clockwise movement. Where is your line of action of the force? Where the point is. Then shoot yourselves towards that point. So plus VA into 2. Then 10 tail to the head towards D. You see 10 is passing through D. So how much it will give? 10 into 0. This is giving 0 moment, this is giving 0 moment, VD is giving 0. Then VA into 2 has to be 0. That means VA has to be 0. Then who will take this 10 sin 45? Vertical component is this fellow, VD. 10 sin 45 down, so VD must be 10 sin 45 up. That means 10 by root 2. Like this, by inspection itself, we should be able to find the reactions. Assume that we didn't understand what we talked, let us say. Now, this is the process you have to make it. Sigma x is equal to 0. Right side positive, left side negative. This is for the people who didn't understand what we talked, say. But this, as far as possible in the exam, we should not do and waste the time. 10 cos 45 is going like this. That means down to the right. You travel from tail to the head, is going like this, means is going right side. So plus 10 cos 45, because any force that acts right side positive. This HA now is acting left side, minus HA must be 0. So HA is 10 cos 45 means 10 by root 2, left side. Cos 45 how much means 1 by root 2, we should be able to get it. Otherwise, take the calculator, where is 10, where is cos, where is 45. Then if you put it, then you calculate, say, then entire time is gone in calculating 10 cos 45 itself. Okay, 10 by root 2 over. Next, take moments of all forces about D is equal to 0. For this sign convention is, if any moment is acting clockwise positive, any moment acts anti-clockwise negative. So HA will give 0 moment because line of action is passing through D. 10 is also passing through D, so 0. So plus VA into 2 plus 10 into 0. Shall we write plus 10 into 0 or minus 10 into 0? Once it is 0, whether it is plus 0, minus 0, doesn't matter. Whether you write minus 10 into 0 or plus 10 into 0, it hardly matters. So VA now has to be 0. But to get this one, so much we should not do and write VA as 0. By inspection itself, 10 into 0, then plus VA into 2 is equal to 0. So, VA has to be 0. Then now can write sigma y is equal to 0. 10 sin forward upward, any force that is acting upward positive, any force that is acting downward negative. So, minus 10 sin 45 because it is acting downward, plus Vd must be 0. So, Vd is equal to 10 sin 45 means 10 root 2 kilonewton. So, this much we should not do and say that the reactions are, this will waste our time in the exam. Assume that now you have understood how to find the support reactions by inspection itself without this one. Now, member forces we want to see. Assume that I want to start from here. VA is 0. Once geometry is cut, throw it out. Now, how many are there? 1, 2, 3. 2 are in line, third has to be 0. Then what is the force in the member? AD. 10 by root 2 left side, arrow mark. On the pin now it should act right side, 10 by root 2. Now you see if arrow mark is away from the joint, far end also arrow must be away from the joint. Over. So 10 by root 2, in one place you write 10 by root 2 enough. This is 0. Now come to joint C. Two non-collinear members, no external load, force in both members are 0. Here 10 down, to balance it 10 up. Arrow towards the joint, same 10. See, by inspection itself, why one member entire force is in the truss members we can find in 1 minute time. So, this is the support reactions we find. Now, we will take some other Now, we will see the next question. Force in the member AC. AB. Assume that this force, let us say 20 kilonewton. This is a roller support. 60 degrees, this is 30 degrees. Okay. We want to find force in member AC. Now, hinge support will give two reactions, VA, HA, here reaction is VC. Okay. Now, once there is a roller support, as you have learned in SM, perpendicular to the plane of roller support, only one reaction, parallel to that reaction not possible, simply rollers roll. When reaction is not possible here, only one reaction can exist here. That one reaction will exist only when there is action. If there is no action, no reaction. So, HA has to be 0 because externally no action is there, horizontal action. So, reaction should be 0. Supposing that here hinge is there, here also hinge is there. Then what happens? There is one more horizontal reaction. Two horizontal reactions are existing, let us say, in a problem. Action is not there, but two horizontal reactions are there. At the most, you can tell that two horizontal reactions are equal individually, they need not be 0. Then both reactions will exist. We have to find by some other means, but now in this case, one reaction is 0 implies that other reaction has to be 0 when there is no action. Now you see, I want to find force in member AC. If I take free body diagram of joint A, how many unknowns are there? AB, AC, VA. VA we don't know. To find the reaction distances they have not given. In that case, what we have to do? Some x, y distances you have to take and interpolate. So, some more extra time we have to waste. But allotted time is only 1 minute. Marks are only 2. So, is the case here. VC we don't know. See, FBC, FAC. So, we will select a joint where only 2 unknowns are there. So, B you can take it. FAB, FAC. FAB I will find, let us say. Once FAB is known to us, I can find FAC from that. Within our stipulated time we can calculate. Now you see, if I want to take free body diagram of joint B, first we will find AB, then AC. If this is 60 degrees, then it has to be 60 degrees. 30 means this has to be 30. Now to find the directions of forces, by inspection itself we can find forces in all members for the simple cases that we get. You see here, to find direction of force in member AB and BC, it's like this. On the truss, somebody is pushing it like this, say. Then how these two members must respond? When I'm pushing it like this, these two members will push him up like this. Otherwise, the pin will not be in equilibrium. So, for pin to be in equilibrium, the two forces, they must be like this. This is force in the member AB. Here also arrow must be towards the joint, here also. Once here towards the joint, here it should be towards the joint. This you can take force in the member BC. But we have no intention to find FBC. If I know FAB, I can find here. Such cases, what we do is this one. We will take free body diagram of joint B. So, joint B now looks like this. This load is 20. This joint is B. 30 degrees, 60 degrees. This is force in the member AB. This is force in the member BC. So, 60, 30, 90 means, so this has to be 90 degrees. Now we see. At a joint, now if I write sigma x is equal to 0 to find FAB, this also will come. FAB cos 60, FBC cos 30 is equal to 0. So, FBC one simultaneous, two unknowns with one equation will get. Then I have to write sigma y 0, FAB sin 60, FBC sin 30 minus 20 is equal to 0. So, I have to solve two simultaneous equations to find FAB, but we don't want to waste that much time. Such cases where you have to use simultaneous equations to find the force in the members, you take the sine rule to finish off the problems quickly. At least 20 or 30 seconds we can save by doing like that. 90 plus 30, what is the total angle here? 120 degrees. 60 already is there, 90. 90 plus 60, this angle is 150. This already we know, 90 degrees. Now, sine rule we can use at a joint, or you can use for three forces which are already in equilibrium and which are concurrent. Now, three forces are concurrent at point B and they are in equilibrium. Now, we can use the sine rule. What is the sine rule? FAB is surrounded by 150, 90. Opposite angle is 120. So, FAB by sine of opposite angle must be equal to 20 is surrounded by 150, 120. Opposite angle is 90. Force by sine of the opposite angle. Force by sine of the opposite angle should be equal. So, that is what is sine rule. Using sine rule, I can write FAB by sine 120 must be equal to 20 by surrounded by 150, 120, opposite angle is 90. 20 sine 90. Sine 90 is 1. So FAB you will get 20 sine 120. You will get around 17.32 kilonewton. Because the arrow mark is towards the joint, it is compression. First, because arrow is towards the joint, you have written compression, not because this compression arrow mark you have kept it towards. First this happened, then this one. Now, once you find that FAB has 17.32, this force is now 17.32. Now we can take free body diagram of joint A. This is the first point. If at all here also you are interested in BC also, let us say, you can write FBC by surrounded by 90, 120, opposite angle is 150, sine 150. You can find FBC also, but we are not interested in that. Then from free body diagram of joint A, what you can write, you see, here arrow mark is going down to the left. It's going like this, means it's going left side and down side. But left side is our interest. It's going left side. To balance this left side arrow mark, here H is already 0. It has to be now right side. Otherwise sigma x 0 will not happen. Like that, by inspection you can fix the arrow mark. Instead of drawing this diagram here again similar to that diagram and wasting the time, there itself we can make use. Sigma x is equal to 0. Right side positive, left side negative. See, this 17.32 cos 60 is going left side. So minus you have to write 17.32 cos 60 plus FAC is equal to 0. So FAC will get around 8.66 kilonewton. Now arrow mark is away from the joint, so tension. In 2 minutes time, your task is this and this. Okay. Now from this you understand this one. Not. To avoid solving simultaneous equations, use sine rule. To find forces in the members quickly. Then when can you use sine rule? To use sine rule, there must be 3 forces. 3 forces which are in equilibrium. And three arrows must be either towards joint or away from the joint. Then we can use the sine rule. Now you see, in this particular case, the 3 arrows are towards the joint, so no negative sign, nothing will come. Or 3 arrows can be away from the joint, no negative signs. Supposing that in a particular problem, these 2 arrows towards, this comes away, let us say. Then arrow mark is away, pluck it out, keep it here, free vector. Then 3 arrows are towards the joint, then no negative sign will come, but forces you will get it directly. Okay. So that's what. That's how you have studied in engineering mechanics. You have studied sine rule, cos rule. Cos rule we use to find theta very fast. Sine rule we use to find the force very fast. No need to use the simultaneous equation. Directly we can use the sine rule to finish off fast. These are some of the techniques to get out of the problems quickly. We should use only such circumstances where you have to use sigma x0 when you are using 2 equations comes here. Then why headache we can use like this. If 4 or 5 forces are there, then you cannot use sine rule. Okay. So that's how we manage this problem quickly. Okay, this is about the method of joints. This to use method of joints, you see very small panels we have taken, only one panel you found the forces. Supposing that if you have a very big truss and in the intermediate member you want to find force, let us say, then from one joint where two unknown members are there, two unknown forces are there, from there you cannot start and go on finding all the member forces, come to the given member, means it will take half an hour time. Such cases where you want to find force in the intermediate member, you can use another method called method of sections, which will let you finish off in again 30 seconds time itself. So, we will see now the method of sections, how we have to solve it.